title of this presentation is Reconstructing a Soviet-era Plastic Model to Predict Vibratory PileDriving Performance. Vibratory technology has been used for both the installation of driven piles and for soil compaction since World War II. For driven piles, the key conundrum in the expansion of the use of this technology, other than the ground vibration issue, which is a whole different subject, has been relating the performance during installation to the axial capacity of the pile during use. With impact-driven piles, this is well developed. For vibratory, we're still working on this. There are several research efforts, most of which are in Europe, that have been going on for at least the last 20 or 25 years to attempt to bridge this gap. At this point, however, there is not a definitive answer which is suitable for use in construction verification. In other words, you drive a vibratory-driven pile, you measure the speed of installation and the size of the hammer, and then you say, well, because of that, the pile has this axial capacity. We're not there yet. The use of the technology goes back a long way, though, and in fact, it was developed in the Soviet Union in the years before and after the Great Patriotic War, which we call World War II. The two researchers who did the most to develop the theory and the application of these methods to driven piles are D.D. Barkam and Yuri Neymark. At the same time, in a parallel development, impact vibration hammers were also developed under S.A. Tseitlin. The first pile-driven and actual work, once we got out of the laboratory of the Research Institute, were flat sheets for a cellular cofferdam for the Gorky hydroelectric project in 1949, which gave very good results. This is a cutaway view of the BT5 vibratory pile driver used with the Gorky projects. There are a few things to note about this. The vibrator number 4 is an electric motor, and that's typical with almost all your Soviet machines, and the Japanese did the same thing years later, as did some of your early Western European machines. Hydraulically driven vibratory hammers were first introduced in the United States in the late 1960s, and hydraulic hammers are pretty much dominate the vibratory market now. Interest in electrical machines is, however, reviving due to environmental concerns. You'll notice at the bottom 12, 13, 11, and 3 show a screw-type pile clamp, which actually is kind of similar to what we used with the impact extractors. These have been replaced with hydraulic clamps. A static suspension, which is sprung connected to the vibrating part of the driver, is now standard on most machines to dampen the vibrations of the crane and to provide additional driving capability. And we'll talk about that as we go along. The basics of vibratory pile driving are deceptively simple. Basically, what it involves is most of them use counter-rotating eccentric weights to produce a vertical sinusoidal force. The horizontal forces are canceled by the way the eccentrics are synchronized. In some cases, they're not synchronized. They're synchronized themselves. The loosening of the soil allows the driver and the pile to sink into the ground by their own weight. The response along the pile shaft and at the pile toe is different. The shaft is most affected by the vibration. In other words, you get the most loosening along the shaft and not so much at the toe. The key parameters in this, and they're shown in the diagram, are the eccentric moment, the frequency, and the dynamic force. Shaft and toe, the diagram in the upper right-hand corner shows the basic free body diagram. You've got a Q, which is a static force downward. The P naught times the sine omega t plus alpha is the dynamic force. And the F is the shaft resistance along the side of the pile, and the R is the toe resistance. And that particular model shows a purely plastic model, which is one we're going to study. The Soviet researchers in the early days modeled that resistance as a unit. And we're going to actually replicate that model. The model was first presented well, actually the first model that was presented in Tseitlin et al., which is in 1987, towards the end of the Soviet Union, is the model we're going to consider in this study. And you can see not only the book cover, but a picture of a Soviet vibrating machine driving piles in Leningrad. There are some assumptions that are important. First, the pile and the vibrating portion of the hammer are one rigid body. And this is still a common assumption for models for non-resonant vibratory drivers. Second, both the shaft resistance and the toe resistance are purely plastic, which they have no elastic or spring component to them. The shaft resistance is bidirectional, which opposes the motion of the pile, and the toe resistance is unidirectional. It only acts when the tile moves into the toe soil, that block with an X in it at the bottom. Static overweight influence does not interact with the pile. In other words, we don't split out the static overweight influence in the model. I dealt with that in a paper about 15 years ago on how that actually works. To implement the model, probably, they don't say so, but probably the original model was probably done by hand, which explains how it was done. It was done on a piecewise basis as opposed to a time-stepping scheme, which we normally use in numerical analysis. The model is programmed using Fortran 77 with a distance of Maple 5. These are old tools, but they get the job done. The model is generalized by the use of dimensionless parameters. This is very similar to the system that I showed with impact hammers in semi-infinite piles. In this case, we have three important ones. Little q is equal to big Q over P, and P is the peak dynamic force. Little f is equal to big F over P, and gamma is equal to R over P. The object was to replicate the cases, or not replicate, depending on how the study came out, cases shown in the original monograph. The original monograph emphasized the net positive downward deflection with each cycle. It's a cyclic model. In other words, it analyzes every rotation of the eccentrics as opposed to trying to set up a continuous. The sinking of vibratory piles looks continuous to the observer, but in fact it is also a cycle by cycle analysis. In this model, power consumption will be considered as well, and we're going to compare it to the simplified viscous model used by the Soviets and many others. The first thing is the Soviets said F is equal to 0.5 constant, and they analyzed, they varied Q from 0.1 to 0.4, and they analyzed the model with gamma either at 0.7, 1.0, and 1.3. And on the left is Tseitlin's depiction of the results, and the right is mine, based on my numerical model. And the results are basically the same. Also, I included an analysis for power parameters. Alpha is a coefficient which represents the relationship between the eccentric moment and the rotational speed on the one hand, and the power consumed on the other. And for a purely viscous model, the peak alpha can be found at 0.25. You can see from this two things. First, on the left, you can see that alpha does not exceed 2.25. It actually decreases from that value as you increase Q, in other words, the static overweight to the static downward force to the system. On the other hand, Y over alpha is the relationship between the advance of the system per unit per cycle and the power. And basically, you see as a rough measure of the utilization of that power. The power utilization improves with the addition of the ways you can see, definitely in the lower toe resistance. In the upper toe resistance, it increases into a point and then it comes back down. We'll see this replicated in more extensive studies. This is a time plot for one cycle. You can see the acceleration, velocity, and displacement. The piecewise nature of the analysis is very clear from this. And that had both pluses and minuses in terms of the analysis. It eliminated a lot of the problems you got with time stepping, but it also has problems of its own. The biggest thing it eliminated is the problem you have with purely plastic models with numerical analysis produce discontinuities. You can actually see those discontinuities, but instead of the discontinuities being spread out over a lot of time steps, they occur at definite points in the analysis. They're anticipated by it. One interesting region is you can see actually in two places where the velocity and the acceleration are zero. One of them is just before the midpoint of it at 3.14 pi radians or 180 degrees, and the other one is towards the end. These the Soviets referred to as parking regions. Now we do a more extensive study where we vary Q and we vary F, and this was something of a mystery to start with. On the left is the Soviets' rendition of this, and those particular numbers refer to different values of gamma. And the problem with this was that it wasn't clear from the Soviets' narrative what this was. Actually implementing the model in this way made it very clear what it was. It is the minimum value of gamma at which the model operates. And as you can see on the right, that's a three-dimensional represented from the model. The blue area has fairly low values of gamma, in some cases very low values of gamma. The gamma that is a minimum gamma that the system requires for this model to work. Now, there are several. You also notice the mangy-looking backside. The mangy-looking backside is partially a function of the graphing software, but it's also, that's kind of a mangy area in terms from an analytical standpoint. That part of the model really has reliability issues. Here, as you approach the origin, things kind of break down. Another mangy-looking thing is in the front. The reason for that is that there's no really defined solution for this along the diagonal, where Q plus F is equal to unity. And that's a consequence of the physics of the system. Theirs include power performance plots. The power alpha, which we looked at before, has a definite peak ridge that decreases on both sides. And you can also see that alpha is actually goes well above the 0.25 maximum for the viscous model. And that's an important result for actual use, and that's probably due more than anything to tow resistance. On the right, the Y over alpha shows that the system is most quote-unquote efficient when the Q is at its greatest, in other words, the greatest static force on it. A displacement variation plot shows a distinct peak around, say, Q of 0.7 or 0.8, and then it goes down in either direction. And again, this shows that there are, as the case with many things with Vibratory, there are really kind of sweet spots that we like to try to get to. Those aren't always easy because of the equipment we have at hand, but they're there. A few comments I've made already. The first, the results of this same for the single value of Q. The survey of Q shows results that are similar, but they're not identical. They're not quite perfect, and that may be due to limitations to the hand solution. This model goes unstable in some very disturbing, largely because of what happens is that the parking regions disappear, or they become negative in length. In other words, the system requires that the velocity and the displacement and everything be zero at the 0 point at the beginning of the cycle. And if there's no parking, if the parking area goes negative at the end, you can't close the loop, so to speak. Again, I think I've observed the rest of those already. Another thing I wanted to do, which is a little bit different subject, is to compare this with the Savinov and Laskin model, which to my knowledge is the first model that's been used to estimate, to actually size vibratory hammer projects. You'll know in my studies, and this comes from an equipment manufacturer, that drivability is for me is the important issue. Other issues are important, but from a manufacturer's standpoint, they want to make sure that the hammer gets the pile on the ground. The model requires that the dynamic force be greater than the shaft resistance. That's not an absolute necessity in this model, but they do that for conservatism's sake. There is a minimum free hanging velocity, which basically means that if there's no resistance, the peak velocity needs to be at the minimum value. And that's the way that the Savin-Alpha scheme forces soil fluidization, which the numerical model doesn't really have a mechanism for doing that. They know if a certain f is really, and a certain relation of little f is there, then it will do a certain thing. They don't know what that relationship really is. The numerical model can, however, estimate the average velocity which the pile penetrates the soil. The Savin-Alpha scheme model doesn't. And the Savin-Alpha scheme model has ranges for acceptable values of Q. Some conclusions is it's the simplest model that is possible for this type of thing. The use of a purely plastic model is the model's greatest weakness. And it creates rigidities in the model that don't really exist in the field. For cohesionless soils, they observe that the elastic portion is not very significant, especially when the pile is moving rapidly. And I think that's a reason for cohesional soils. That's a reasonable assumption. For cohesive soils, it's different. Power consumption estimates justify having the power available, which is larger than the viscous model. The viscous model is not the final word. American manufacturers discovered this and adapted to it, but had no theoretical basis to do so. This provides a theoretical basis which, if the Soviets had adopted it, might have changed it, but then again, it might not have. The schema is conservative, which is okay if you're trying to make sure your hammer gets piles in the ground, but it does not estimate the velocity of the pile. As a postscript, Tseitlin and Al have other parts of this, and all of this is available on my website. They do an issue of purely plastic. So you see the diagram on the right, there's a little spring C3 down there. Unfortunately, they set that model up in such a way that the bottom plug, the thing with an X in it, doesn't move. So it's not very useful for penetration velocities and that kind of thing. It goes to a steady state, and that bounces at a steady state, and that's pretty much the end of it. They do propose models which allow for elastoplastic results of both shaft and the toe, and do not present any results. They also discuss a model which allows for wave propagation in piles and different soil properties, different layers, which is remarkable because the Russians never really, in the Soviet era, never really took to the wave equation. That was a development that started in my document and many of my publications elsewhere. But it was mostly started in Australia and moved to the UK and Sweden, and from there the United States. In models going forward, we will include elastic, we will include strain softening capabilities, we will include many things that were not in this model, but this was a start, and I thought it was useful to go back and look at it. For further information, visit my website, vulcanhammer.info, which includes this paper, plus it includes the Tseitlin, Verstoff, and Asbell's book, or parts of it, in English translation, which will give you a more idea of what's going on. So, thanks for watching, and God bless.